Hello, I'm stupid. I forgot to record. We just learned this. This is conservation of baryon and lepton number. Those are baryon numbers and lepton numbers. We're about to answer some questions on it. Thank you for joining us, random people on the internet. Hopefully my students, primarily, if you ever watch this, which I know a lot of you don't. Speaking of, if you haven't filled out that survey yet, I emailed you a survey about how much you were using the digital stuff. Only 7 people out of my whole class responded. It was ages ago, but then didn't I resend it, or did I just remind you that I had sent it? I reminded, or I resent it? I did resend it. I emailed it to you again, being like, yeah, you might have, yeah. Some people had already done it. Let's do a check for understanding. Okay, so find the baryon number for, and again, you won't be asked this question on the exam, all right? No, but you do sort of need to know what to expect with baryon number, and you need to know whether it's conserved or not. You don't have to get that from a quantitative approach, but it's the best way to do it, so. You've never heard of a kaon before, but you have now. It's a type of meson. Strange and an anti-up. All right, nice quick little check for understanding. We'll go through answers in a minute. All right, let's go through answers. Down, down, up, yep. Or up, down, down. Or up, down, up. Or down, up, up. Get the point. Charm particle, B equals a third, 1 quark. 1/3 of 0 minus 1, or 1 minus 0, sorry. 1/3. Anti-bottom particle, B equals -1/3. Proton, 3 quarks, no anti-quarks, 3/3, B equals 1. Anti-neutron, B equals -1. Positron, B equals 0. Positron has no quarks, it's an anti-lepton. Kaon meson. It's a meson, which means it's 1 quark, 1 anti-quark, which means it has a baryon number of. Make sense? Now, this has to be conserved, right? So if you start with a charm particle, you can't just make a proton, right? That seems obvious. If you start with a proton, you can't just make an anti-neutron. Baryon number's not conserved. What you have at the start, you have to have at the end. And that's how all of these antiparticles and the neutrinos and all of these things interact to make this work. Lepton number for tau particle, which is just 1 lepton, L equals 1. Yep, leptons don't make composite particles, so it's not baryon number or some sort of hadron version of leptons, it's just the leptons. So when you have 1 lepton, you have a lepton number of 1. Tau anti-neutrino, -1. Neutrinos are still leptons. They're chargeless leptons. So an anti-lepton is -1. And a proton, right, of course, has no leptons. You can obviously imagine yourself extending this into a hydrogen atom, a helium atom, etc. Count the protons, count the neutrons, count the electrons, figure out the baryon and lepton numbers, smash them into pieces in a particle collider with another particle, add up all the baryons, all the leptons, see what you should have at the end. If something's missing, you know you're looking for a particle. And this is the exact process that they did. They smashed things together and they calculated that they would expect this thing to be conserved, and there was stuff missing. And they were like, how can that be? There must be something there. And they looked and looked and looked, and they found it. That's how they discovered things like the Higgs boson and a lot of these elementary particles. Neutrinos were obviously very difficult to detect, being so small and being chargeless. So yeah, so you can appreciate the importance of conservation of number. So let's do an example where we conserve some number in some interactions. Example. All right, I'm going to use pen, not text. Check if baryon and lepton number are conserved, the below interaction. Interaction shall be proton decays into neutron, positron, and an electron neutrino. Anyone know what this is? Beta decay. Do you remember if it's beta positive or beta minus? Which way around we defined it? Minus because it is. Honestly, I could not say 100% I remember. I'm pretty sure it's I'm pretty sure it's beta positive because the emission is a positive emission. But it can be the other way. I can't remember which way it was. I'm shocking for that sort of thing. So proton decays into a neutron, and a positron, anti-electron, and a electron neutrino. Now notice that the electron is an anti-electron, a positron, right? I'm talking about this. I know what I'm saying right now is a bit confusing. This is the antiparticle here. Notice that the neutrino is not an antiparticle. Now, if you're thinking in your head's lepton number, you should be going, oh, well, that I see why. Like, that makes sense, okay? And if you're not seeing that yet, let's do it. No, I do not. B equals a third of Q, NQ, sorry, NQ minus NQ bar. Third of, how many quarks does a proton have? 3. How many quarks does how many antiquarks does a proton have? None. So baryon number before, let's say BI, B initial, equals 1. Find a B final. And hopefully you can see why I don't really care whether you do the math or not. Really obvious math. How many quarks does a neutron have? The baryon, it has 3. How many antiquarks? Baryon number of 1. Is baryon number conserved? Bi equals Bf. Tick. How many leptons are present initially? 0. How many leptons are present finally? How many leptons? 1. How many anti-leptons? 1 minus 1. So what does that tell us? It's all conserved. That interaction is entirely plausible. Yeah? If we see a proton decay into a neutron, we should be finding a positron and a neutrino, electron neutrino. If we don't find a positron and an electron neutrino, we either didn't measure them properly or something's gone wrong somehow, because these are always conserved. Got 13 minutes left. I feel like that's it. Like, your textbook goes into a lot more detail, but honestly, there's not much to this. Give you a couple of questions just to check, and then we'll pack up. Silent ball. Hang on. You need to finish your. Do you remember the state of your card game? The exact. You remember the state of the board, the exact positions of everything. Do this first. Tell me. Pi negative meson has a quark composition in UD. It reacts with the proton to produce. This is a messy one, but I like it. Determine whether the reaction will violate baryon or lepton laws. This is about as hard of a question as you could possibly get with this. And again, I really don't think you'll struggle too much. So pi negative meson, just a type of meson. You can call it a pi meson for all I care. There's a pi positive and a pi negative. They're the antiparticles of each other, anti-mesons of each other. So pi negative meson, which just is a meson with up, anti-down. It reacts with the proton, which is up, up, down, to produce a kappa 0 meson. There's the symbol. I don't even know what that symbol is. Is that a printing error? I think that's a printing error for the... Anyway, whatever. All you care about is the quarks. So down and anti-strange. And a lambda 0 baryon, which is a new type of baryon. Up, down, strange. You might have made it when you played the card game the other day. Up, down, strange. Anyone remember making a lambda 0 baryon. Did I have any kappa 0 mesons in the house? Sorry, I'll stop. According to the following equation, that becomes that. That plus that becomes that. Let me rewrite these things. So here's what you care about. That's something's definitely gone wrong with the printing. Wow, I've never noticed that before. All you care about is UD. Is it U anti-D? Up, anti-down, plus proton, which is UUD, produces. You can just use an arrow or whatever. There's a bit of a convention of a squiggly line for decays or reactions and stuff. It doesn't actually matter. To produce kappa 0 meson, which is down anti-strange, and a lambda 0 baryon, which is UDS. Okay. Determine whether the reaction would violate the baryon and lepton conservation laws. Such an ugly problem.